Hello everyone, I'm Zili Zhang, an undergraduate student from Peking University. Today I'm glad to share our work, fast approximate vector queries on very large unstructured datasets. This is a joint work with Chao, Xuanzhe, and Xing from Peking University, and Linpeng from Moqi. Before introducing our system, I would like to introduce you some background about vector search. Vector search uses machine learning to translate the similarity of text, image, or audios into a vector space, and processes pairwise distance evaluation to find the nearest label vectors for query vector. As shown by this animation, there are some black points denoted as the database vectors. The orange point represents a query vector from users. Vector search is aimed to find the top k nearest vectors as soon as possible. In this example, the system should return the blue point as the top one result. Vector search is adopted in many real-world AI applications like information retrieval, face recognition, and recommendation. It has the general workflow as shown in this animation. Here, we have plenty of database items marked as blue, such as text, images, and videos. These items are converted into high-dimensional feature vectors through the embedding layers of deep learning models. Offline, online, the user provides an input query, which is first converted into a query vector through the same model. Then, the system performs vector search among the database vectors to find the top k nearest results as the classification results. As the scale of the database item grows up to billion and even trillion, the vector search becomes the key bottleneck in this workflow. As we discussed above, exact vector search processes pairwise distance evaluation between query and the database vector one by one, which introduces high query latency and violates the strict SLO for some interactive jobs. Besides, when converting the unstructured items, the deep learning is not able to produce the exact vector result. Thus, approximate vector search is widely adopted in production and academia. There are many approximate vector search algorithms. One of the most widespread and effective is inverted file index. While IVF have many variants, it has the following general workflow. At offline, it collects the database vectors and partitions the vectors into several clusters through k-means. As shown by this animation, the points are partitioned into 5 clusters, cluster 1 to cluster 5. Online, given a query vector, IVF processes pairwise distance computation only in the top n nearest clusters rather than all clusters. For instance, for the query vector, searching in the top 1 cluster, cluster 1, is enough to get the exact top 1 result, but it saves around 5 times on searching than the exact vector search. So the parameter top n decides the query latency and accuracy. As shown in this figure, as top n grows, the latency and accuracy both increase. The accuracy will at last converge to 100% after processing all database vectors. But existing vector database leaves tuning the top n to users. The users are unfamiliar with the underlying approximate algorithm, and they suffer from tuning the top n in IVF. What they really focus is the query performance, such as latency to meet the strict SLO and the error of vector search to meet the final result accuracy. They are looking forward to using a vector search system which provides bounded performance and allows the users to specify a time or error bound. For time bound, the system should maximize the query accuracy within the time budget. For error bound, the system should minimize the query latency within the error budget. In our paper, we propose Auncel, the first distributed vector search engine that provides bounded performance, which is more user-friendly and efficient. Auncel allows the user to specify a time or error bound. For time bound, it maximizes the accuracy within the time budget, and for error bound, it maximizes the query latency. Auncel is also a distributed solution that calibrates the distributed configuration to guarantee the error bound in distributed settings. Before introducing our system, I will introduce some baseline methods to guarantee the bounded performance. Providing the error bound is challenging since the relationship between error and top n is hard to provide. Phase is a widely used open-source vector query processing engine and is adopted in production-level vector database like Mavos, Zili, and Peking. Phase adopts a simple method to tune the top-N parameter in order to provide bounded performance. It samples some queries to process vector search under different configurations of top-N, and records the bounded error of each top-N in the sample queries. After processing the sample queries, it maps the error bound to the corresponding top-N as shown in this figure. Online, it is able to process vector search under an appropriate top-N to meet the user's requirements according to this map. However, this method ignores the characteristics of individual queries and uses a fixed top-N for all queries under a given error bound. To guarantee the bounded error, the system should apply the top-N of the worst case for all queries. As shown in this figure, the worst case is query 2, which introduces 10 times redundant computation in this example. So this approach is query agnostic. Another baseline is learned adaptive early termination. LAET leverages a gradient boosting decision tree to predict the top-N for different queries. It samples some queries and processes the vector search to train the decision tree model, but the model ignores the underlying geometric characteristics between the database vectors and the query vectors in high-dimensional space. So the predicted results is far from the optimal. As a result, LAET needs a very large multiplier of top-N for all queries to guarantee the bounded error. As shown in this figure, query 6 has the highest multiplier and introduces severe redundant computation for other queries. To improve the prediction accuracy, we can include a complex ML model, but it may introduce large overhead for prediction on CPUs. So the black box fitting is not appropriate for profiling the error bound. Our system Auncel provides the query error after searching each cluster. If the error satisfies the specified error bound, Auncel terminates the query and returns the intermediate result. In this example, Auncel terminates the query processing after processing cluster 2, and it does not process cluster 3. As for the error profile, Auncel leverages white box high-dimensional geometry to predict the error. As shown in this animation, the query locates in cluster 1, and the top 3 nearest labels located in cluster 1, cluster 2, and cluster 3 respectively. The top 3 nearest labels forms a high-dimensional sphere. The vectors within the sphere is one of the elements of the top 3 nearest labels. The sphere is split into 3 parts, part 1, part 2, and part 3, by the 3 clusters. N represents the number of the vectors. Apparently, the error after processing cluster 1 is calculated through the simple formula 1 minus n part 1 divided by top k. It is easy to extend the formula to a general formula. The challenge is now becoming how to predict the number of vectors within the specific part. Our key observation here is that the vectors follow the local uniform distribution in real world, and the number of the vectors can be calculated by its volume multiplied the fixed density. And you can find the validation of such distribution in our paper. As a result, the number is replaced by its volume, which can be calculated through integral in high-dimensional space. And you can check our paper for more details in guaranteeing the bound of such formula of geometric volumes. As for the time bound, guaranteeing the time bound is easy to implement. Our goal is to minimize the error within a time budget. We maintain a global timer to track the use time for a given query. If the use time plus the time for processing the next cluster is greater than the given time budget, the query should be terminated. The time for processing the next cluster is provided from the job history. The general method for distributed vector search is starting the dataset into several loads, and it processes the vector search on different loads in parallel and merges the intermediate results for each load. As shown in this figure, the dataset is sharded into 3 parts, and we can get the final exact top 3 nearest label vectors, number 1, number 2, and number 3, through the exact search. But when facing approximate vector search, as shown in the right figure, each load has an error of 33%. However, when merging the intermediate results, the error is amplified as 67%. Such error amplification may violate the global error bound. To mitigate the problem, Auncel calibrates the request error from each node. It reduces the error for each node by 1 in top k each time. Then Auncel will test if the amplified error in worst case violates the global request error. If the request error is guaranteed, the system will distribute the calibrated error to each node. For example, the request error is specified as 40% by users. The system calibrates the error as 20% in this case. The two intermediate results has at least 3 hidden elements, and the request error bound is guaranteed. With this design, we implement a prototype of Auncel with about 3,000 lines of code in C++ and integrated with Face. Our evaluation is performed on a C5.4x0 instance in AWS and 4 C5.meta instance to support the billion-scale datasets. We use the 4-vector database for evaluation, SIFT, GIST, and DEEP with 1 billion of items, which are converted from images through different ML models. And the text dataset is converted by multimodal. And our baseline system is Face and LAET. First, we compare our system with 2 baseline systems in the end-to-end latency. To achieve fair comparison, we keep the error bound for all systems, and we vary the datasets, error bounds, and top key values to evaluate our system under different scenarios. The result demonstrates that Auncel achieves 3 times lower latency in average than the baseline systems, and outperforms the baselines under various configurations. We also conduct some experiments to evaluate the effectiveness to guarantee the bounded performance. We first vary the different request error bounds and keep the other configuration the same. The results show that Auncel is able to guarantee the error bounds. As we increase the errors, the measured actual error increases as well, indicating that Auncel adapts to different request errors. As for time bound, we conduct the same experiments as the error bounds. The figure shows the results of the maximum and minimum end-to-end query latencies. The results show that each query is terminated before the time bound. To show the benefit of error calibration in distributed settings, we vary the number of the workers to test the scalability of Auncel. We fix the request error as 10%, and the calibrated error is slightly larger than the request error. The results show that the latency is reduced by half when the number of the workers is doubled, when guaranteeing the bounded error, which demonstrates that Auncel is able to scale ideally. Our paper also has many more experiments, including validation of the mathematical formulation and the local uniform distribution, the overhead of runtime profile and system building time. You can check our paper for more details. To conclude, Auncel is a fast approximate vector query engine on very large unstructured datasets. It proposes white box and query-aware error latency profile to guarantee the bounded performance, and applies probability theory to calibrate the error bounds and scale to multiple workers ideally. That's all. Thanks for listening.